Thank you, Brandon, for sharing so many concrete examples. Think as an admin, not a programmer, is a great insight when it comes to perf work. Observability is not only needed for software, but also for hardware. This community is used to solve performance problem with software on top of generic hardware. But with the exploding usage of AI and video, we need application-specific hardware to push performance to next level. Our next speaker today is Coutinho from Facebook. He will talk about how we build observability into AI and video accelerators. Let's welcome Brian.
Hi, I'm Brian. I'm dialing in from the Bay Area. As you can see, I have an interest in music and in science fiction books as well. And that's one of the reasons why I find this topic very interesting. We're going to talk about observability for artificial intelligence and video accelerators. So I'd like to kind of give you a high-level overview of what AI and video accelerators are and the origin story behind them before we get into the topic of observability. So let's kind of start a little bit into the history of AI technologies and AI models in general. As we all agree, AI is one of the most transformative technologies of our current times. And surprisingly, like the origin of neural networks actually started around the 60s, where we had the first simple neural networks coming up. So on this chart, we're actually looking at various popular AI models across time. And where on the y-axis, we plotted the amount of computational complexity required to train and run these models. And note that this axis is actually a logarithmic axis. So right from the bottom to the top, it's like 10 orders of magnitude. So right at the bottom, you might represent a very old mobile phone. And right at the top, it could be something like hundreds of cutting-edge servers put together. So from the 1960s till now, we've had amazing advancements in AI. So essentially, we've been able to recognize objects, we're able to translate between various languages, we're able to defeat humans at a very complex strategy game like Go. And all of this has been enabled by this advance of AI hardware. So as we can see, there's this inflection point around around 2010, where AI models have suddenly been growing at higher complexity relative to the past. So the reason for that essentially is introduction of new accelerator hardware. So before 2010, we had CPUs or general purpose processors that were actually enabling AI. But in the recent years, we've been able to make more gains with the help of specialized hardware that helps accelerate AI applications. And this relationship works both ways. You need advanced AI hardware to run these complex models, and you also need advanced hardware to actually design and dream up and come up with these new AI models as well. Why do we care about this at Facebook? Well, of course, we invest heavily on research in AI, and we use AI in our products, but we also use AI on integrity applications for the social media platform. For example, we use it to take down fake profiles. We use AI models to interpret videos and flag things that are harmful. Since Facebook supports like 2 billion users, there's a huge demand for AI at the Facebook infrastructure. So the Facebook AI infrastructure runs about 150 trillion AI predictions a day. That's 150 million predictions. And that's a huge amount of demand on the infrastructure. And there's a trend of more adoption of these AI models at internal teams in Facebook. In fact, this is a recently published paper where we've shown that more and more teams have been adopting workflows that use AI models. So given these two trends and the complexity of the hardware required to execute these AI models, we've been building systems that essentially can accelerate AI applications. So an AI accelerator, or an ASIC, short for application-specific integrated circuit, this is just special hardware that's designed to run AI applications faster. So we built the first generation of these systems at our data center, and that's already delivered 10 to 30 times higher performance than the CPU. And because this is customized hardware, so it also is more energy efficient, and we're able to get like 3 to 10 times better energy and power efficiency as well. So switching gears a bit, we also have another application that's on the rise in our infrastructure, and at Facebook and Instagram, and those are videos. So essentially, we have about 250 million videos uploaded daily at the site, and we need to encode these videos in various formats at various bit rates because the apps can dynamically switch bitrate they use based on your network connectivity. So we've been investing on video accelerators that can help accelerate video transcoding, and they've been able to achieve like 10 times higher performance over the CPU. So putting these two trends together, we've essentially built a server that can handle these special purpose accelerators. And the server essentially has two CPUs or twin lake servers. And attached to each one of them, we have multiple accelerators connected over a PCI switch. These accelerators are shown here as M.2. That's essentially just a form factor specification. So you can see in that small picture, it's kind of like this piece which you could slide into the server. So that's basically the idea there. And in terms of the investment that we've been doing, we started this work in 2019, and we've already built like a first generation of AI and video accelerators. And in 2021, we're also working on the second generation of ASIC chips for the same. So there's a lot of investment at our infrastructure on hardware acceleration. This brings us to the topic of observability. So why do we really need observability? As we're operating a data center with hundred thousands of these accelerator chips, we really need software to kind of understand and track how they're performing. You need to understand, how they are running in terms of health, make sure that they don't burn up. You also need to be able to monitor the performance of these accelerator systems as well. And then in case the performance changes, you want to also be able to debug why the performance is bad, and you want to profile these systems. And these are all of the various good reasons to have observability for these new systems. There's one additional challenge with building an observability framework for these accelerators, and it's just the diversity. We have two generations of accelerators coming in, one for video, one for accelerator, and like two different phases. So that means we may have 2 to 4 different chips running, and each of them may have their own driver and their own interfaces. So we don't want to get into a situation where we have a lot of duplicate software, and we make it really hard for people to develop and build these observability features. So that brings me to the topic of the observability framework that we've designed, and it's called Asimov, which, as the name explains, it's essentially an ASIC monitor or an accelerator monitor. And we built it around 3 objectives. So the first one was to make sure that it provided abstraction. Essentially, it was able to hide all of the details of the accelerators running underneath. And in this way, anyone who uses Asimov doesn't need to know what accelerator is running. And they have a standard API to access them. We also wanted to make this framework very lightweight and performant so that it doesn't interfere with the cloud applications running on these servers. And then lastly, we wanted to make this very easy to develop with so that new teams could actually add an accelerator in a shorter time frame. So we've been able to achieve enabling a new accelerator in like an order of weeks rather than in months. And I think that's a pretty significant achievement. So when you talk about abstraction, I think this diagram very clearly explains how Asimov is actually hiding and abstracting the details of the various accelerator hardware. So we have like various video and inference chips, and each of them may have different APIs that, some of them may be through Linux sysfs, some of them may be through some profiling library. And Asimov is kind of hiding all of this complexity, and it's providing a standard interface so that all of our observability software can be built on top of it. So for instance, on the left, we have like a stack of health monitoring software that's able to kind of figure out when an ASIC is running bad or is like faulty, and then we can reset it or send it into repair. And on the right-hand side, we have performance monitoring. So you can use this to track the efficiency with which these accelerators are running. You could use it to automatically balance the load. That's something we're going to talk about pretty quickly. No, so we've kind of like solved the problem of abstraction with Asimov, but then basically we've pushed all the complexity down into the Asimov layer. And now what we want to do is we also want to make development within Asimov faster and more easy for like anyone who wants to build observability for a new accelerator. At the same time, we want it to be very fast and efficient as well. So that's where we built the next technology or tool, which is called Asimov. And Asimov essentially is this specification language which allows us to generate the monitoring modules for Asimov. So if you look at the internals of Asicmon, we basically have like a module that's specially designed for running on an accelerator. And what we've done is like we've used Asimov to automatically generate the code for that module. So in this way, this kind of handles all the complexity of managing threads and like reading and caching the data and so on, and exporting the data to other systems. So Asimov basically allows us to focus on the main part, which is reading these metrics from the driver, combining them if we need to, and then building like these derived metrics. So like in this first example here, we're kind of reading various Sisyphus files, and then we're assigning them to standard metrics on the Asimov interface. Then on the second example here, we're we can see that we're actually calling a C library, picking up metrics from there, and then we're defining a derived metric called the device utilization. And this is kind of putting a formula over there, so it's kind of combining the use time and the total time. And as in a sense, it gives us an idea of how busy an accelerator really is. So we basically write config files using Asimov, and then we built a compiler that would take this config file and convert it into optimized C++ code that could handle all of the good things like thread safety and caching and so on. And then this would eventually get linked into the Asicmon library. So I'm going to go through two quick examples of how Asicmon and Asimov have actually been used today in the Generation 1 accelerators. So remember we talked about the device utilization metric. So that metric can actually be used to figure out how busy an accelerator is. And we can use that to kind of scale up the number of instances of an AI model that we're running. So in this chart, I'm actually showing the number of AI model instances. And you can see that periodically you have these spikes, which are essentially times when the model is getting updated. And then towards the end, we have this level shift in traffic. And so you'd see like this device utilization go up. And so then that system will respond and it'll spawn new instances. And so you have a rise in the number of instances of this AI model. Another way that Asimov has really come out to be useful is onboarding new accelerators. So this is a picture of a hackathon we had in January 2020. And we basically sat down for like a few days, like about a week. And we initially had just 30% support for metrics for a new accelerator. And by the end of the week, we could get to like 75%, which is really good enough. And that's a really quick speed of development, I would say. And also a quick note that this is in January, so just before the pandemic. So now that we've actually developed systems to observe performance metrics and health metrics, the next step is really to understand or to answer questions like why the performance is going bad. So imagine like you are a software engineer and you're running like AI model that's running on these systems, and you want to debug, your model suddenly runs 10% slower, and you need to figure out why that's happening. So if I go back to that system diagram, like it has a CPU, it has a PCIe switch, it has an accelerator. The CPU has this whole software framework, which consists of a compiler, Glow, which is essentially a graph lowering compiler that logs, that basically transforms the graph to run on the accelerator. And even the accelerator itself has like software that's running, we have scheduling, we have data moving to and fro. And it's not very easy to understand what's happening in the system. So the solution to this essentially is tracing. And tracing, put it really simply, it's just tracking various events happening across time and across various parts of the system. So for instance, on CPU, we have threads running and we have these various functions that are executing. And then you can see operations happening on the accelerator. And you can also track data going to and fro the accelerator as well. So we took the native tracing capabilities of the accelerator and we kind of built a system on top of it. And the idea was to basically serve two types of users. One were people who were developing new models and, like basically tinkering with them and making them run faster. The second were production engineers and software and efficiency engineers who are trying to debug why a model is running slow on production as well. So we combined both those flows, and we have a way by which you could trigger a trace remotely, and then you would collect and store it in a remote central storage, and then automatically process that trace. So when you collect such a trace, the first thing you can do is actually look at a summary of the trace. So this is a very popular trace summary view where you'll essentially look at the amount of time spent by different AI operations on the accelerator. So for instance, this could help you figure out, which operation should I focus on to kind of optimize and reduce the execution time. We can also use these breakdowns to kind of debug performance regressions between different versions of the model, for instance. And then for the experts who want to dive deeper into the trace, we can also visualize it using like various visualization tools. And we built in analysis to figure out what's the critical path. So in this diagram, we actually have highlighted the critical path of operations. And this helps you figure out which operator you need to optimize or maybe split or break down, for example. So using this, we've been able to close like a 10% performance gap between Cafe2 and PyTorch implementations of one of our largest AI models. And in general, this has proved to be a really useful tool for observing what's happening on the system. So one additional step beyond just the accelerator, we've also been working on correlating events happening on the CPU side. For instance, most of our AI models run PyTorch, and PyTorch framework itself has various types of events. And we've built like this correlation between what's happening on PyTorch and on our Glow compiler on the CPU side, and then what's happening on events happening on the accelerator side. And we could draw these correlation edges. So in this way, if you have an AI graph, which is like running half on CPU and then a bit maybe on the accelerator and then back on the CPU, you can actually track the whole flow. And you can kind of figure out where there are bottlenecks or which ways you can actually optimize this system end to end. This is just the beginning. We're also going to be working on improving our tracing infrastructure. And we are planning to like incorporate other sources of traces like the kernel or eBPF traces. And we're hoping to also like improve our analysis and visualization tools. For instance, we are planning to integrate with tools like TensorBoard, which are open source and a lot of AI developers use them. We're also, a second item is we're also looking at trying to understand this in a distributed context using distributed tracing. So since we know that the application doesn't run in an isolated manner, but you have requests coming in from like multiple servers. So we want to trace the whole flow end to end, and in that way we can like debug latency issues better. And lastly, we're also working with the open compute community to kind of build a specification for monitoring and observing accelerators. So in this way, there are a lot of companies building accelerators. They basically have the basic set of metrics that you would need to run them in a data center. So that's all for me for this talk. I really wanted to give a huge shout out to my team and to all of the folks at Facebook who have been working on enabling accelerator systems. And thank you so much for listening and tuning into this talk.